Alright, as I said guys, we're going to be studying birth and death of stars today, so if you want to, you find this will be on Edmodo. I've already said that anyway. Okay, now, the most important thing that you're going to find out is that stars are mainly made up of hydrogen and helium. Hydrogen being the most simplest atom that we know. Can you remember how many protons are in helium?
2. 4.
1. Sorry, my mistake. 2 is in helium. How many in hydrogen?
1.
1's in hydrogen. Okay. It says there they may look small, but because they are a long way away, this is a star. Okay, but in fact they're bigger and brighter than the sun. Okay, every star in the centre of a star has nuclear fusion. Who can tell me what nuclear fusion actually is?
Two thingies getting joined.
2 thingies getting joined. Okay, so if we have hydrogen and another hydrogen, they get joined together. Anyone know what that would make?
Helium.
That would make helium. So that is what's happening inside the sun. We get a nuclear reaction. That process right here is called fusion. Nuclear fusion. That's nuclear fusion. That would make number 4. Okay? So, also, there are lots and lots of different colours that a sun can be. A star can be. Well, I keep calling it the sun because that's what we know it is. Okay, what's a galaxy? Now, is it going to be...
Stars all joined together.
Correct. It's a whole bunch of stars. And what are stars?
Big gases.
Okay. Here's something, guys, that I cannot comprehend. That I am sorry, go back one. Here's something that I cannot comprehend. There are 80 to 100 billion galaxies. And each galaxy has billions or trillions of stars.
That's crazy.
Yeah, okay. That's hard to grasp. Every galaxy, for example, our Milky Way galaxy that we live in, our galaxy, has billions or trillions of stars in that one galaxy. But there are also 80 to 100 billion different galaxies again. So how many stars are there? Well, it's 100 billion times a trillion
That's crazy.
stars. And each one of them has the potential to have its own planets going around it. Incredible. Incredible. All right. We'll keep moving on. Okay. Hubble. Ladies. Hubble was an astronomer. He designed a whole range of things, but he had something very special named after him, and it's this telescope. Hubble. That's his name. He had a telescope, it was built, and it's actually sitting and orbiting around the Earth. And the reason being is, say, for example, if we have the Earth there, we actually have this, it looks like a big long cylinder, and it's got 2 wings on it, 2 solar panels on it, and that's orbiting around, that's going around the Earth. And what it's doing is basically, it's looking out at stars. Can someone tell me why they would put a telescope out in the orbit of the Earth?
So it could just keep going around.
Oh, yeah, but so the Earth keeps going around too.
So it doesn't get, like, the picture doesn't get flashed out by light.
Yeah, the picture doesn't get distorted. You and I both know that when you're in the city, do you see the stars at night time?
No.
No, it's too much ambient light. Clouds, dust in the atmosphere, all that type of stuff makes our images of our stars and planets like that become very fuzzy. So what they did, they put a telescope out in space. Now, when they did that, they actually are able to get pictures like this. Now, these are real pictures. These are not computer-generated images. These are real pictures. And you can see it says 5 galaxies, Hickson Compact GP52. Hickson Compact GP52 means that's its name. The reason being, why did we say yesterday they called me strange names? Because there's too many of them out there. They give them the name of Bob, Harold, Frida. So they give them these names. All right.
Wait, so they're all different galaxies?
They are all different. Each
But
one.
they're so close.
So each one of these, each one of those has 80, up to billions or trillions of stars.
What's the fifth?
1, 2, 3, 4. I think it could be that part there.
They're so close. But asteroid. But
They are so close because you're looking, for example, if I look straight through you, I see 1, 2, 3. You go, oh, they're so close. But if I look sideways, you're further apart. So you're not seeing depth there, are you? So these are what we see out there. Now, interacting galaxy pair. Interacting, the reason they say they're interacting is if you can see very carefully, there's a section through here. You can see that? Okay, one is actually being like this spiral galaxy. The spiral galaxy here is rotating in that direction, and the reason I can see the arms, but this part of the spiral here is actually being sucked away, isn't it? Who can is actually being who can see it being absorbed, also getting caught in it? Okay, and there's another galaxy sitting over there. So even though that may, now that's not talking 100 kilometres apart.
That would be.
You know, that distance across there and there might be, say, 100 light years. 100 light years is how far light would travel in 100 years. For example, light travels from the sun. How fast does it go from the sun to here? 8.5 minutes from the sunlight to get from the sun to us at the same speed, 100 years. That's a massive distance. So that's not happening overnight. Okay? Not happening overnight. Okay. Okay, the sun's one of the stars in the Milky Way galaxy. The Milky Way contains roughly 200 billion stars in the Milky Way galaxy. Cannot understand that. How do they know it? It's an estimation. Based upon, they take a grouping, for example, they might count a section, and they just say, do like, and add up how many sections there are. Okay?
So that might only be 198 billion.
Correct, Harry. The 2 billion is not going to make too much difference. Okay. Now, why is that an artist's impression of the Milky Way galaxy? If you listened the other day, you would know, Harry.
Because you can't actually, they haven't been outside of the Milky Way.
No. We are located somewhere about here. We're located somewhere about here, and therefore we have not been around. We have not gotten a little spaceship and flown around here to have a look.
Why not?
Because because our next closest star to us, inside that whole galaxy, our next closest star inside all of that is 4.5 light years away. Which means you can't even see the next closest star there, because it's just a blur. Okay? Rightio.
Get robots.
Now, here's something that I didn't think we could have done. That's an infrared image of the galaxy. What it's doing is, that's a satellite that has looked side on through our galaxy, and that's what it's seeing.
So that's a galaxy.
That's an actual photo of the Milky Way. Because they've got a satellite and it's looked side onto it. So it's actually sitting, that's a photo of it sitting inside it and looking through. Okay, we'll keep going. There's another spiral galaxy. By the way, all these things here could also be what? They could be other galaxies themselves. But they're so far away and so big and bright, they look like just a single object. All right? So, all these things existing out there. What I want to do now, though, guys, look at how a star is born. Because this is what you do need to know. Okay. Giant clouds of dust and gas. You call that, and it's called a nebula. Giant clouds. I'm not talking about a couple of kilometres across. I'm talking maybe a couple of thousand light years across of dust particles. And so much dust that you can visibly see it. Okay. What happens next? Now, have a look at that one. That's a real image. That's a real image. ladies. The nebula called the NGC 6302, what resembles butterfly wings, are actually boiling cauldrons of gases heated up to more than 3,600 degrees Fahrenheit. Okay, which minus 36,000, sorry, thank you. Which might as well say about say 12, 13,000 degrees Celsius. Now, what you will notice is it's spewing out in both directions. This is massive. This is a massive thing. So it's boiling. Very hot. Clouds of gas that are extremely, extremely hot. Here's another one. It's called the Hourglass Nebula. Now, what you will notice is they call it the Hourglass Nebula because if you realise an hourglass... Whoop, that's no good. Yeah. How about I do this again? Okay, that's what an hourglass basically looks like. The point of trying to be in the centre here, it's very, very concentrated. Concentrated dust. And basically it's gradually all getting sucked into the centre. Okay? Now this is not going to happen overnight. In fact, scientists would not most likely notice any difference between the time they've lived and died. Because it happens very slowly. Now, sometimes part of the cloud shrinks and forms a ball. Girls, forms a ball and pulls the gas and dust particles close and close together. Okay, here's the important part that we can understand. That there. The gas and dust inside the ball bump into one another, causing the temperature to rise. Friction, in other words. A bit like a blacksmith hitting a bar. Has anyone here ever drilled, put a screw into a wall or taken a screw out of a wall and then felt the screw after it's been really hard to get out? And found the screw is hot? Because of friction. Friction causes the heat. So when these things get closer and closer, they get heat. Now, here's the most important part. Electrons are stripped off the atoms of the hydrogen. So you've got this hydrogen, one proton, one electron. It's so hot, the electron disappears. Which means, what does that hydrogen get turned into? It has a special name now. Say it again, Eli.
Positive hydrogen.
So close. Positive, we say starts with an I. Positive ion. Now, they move faster and faster, crashing into each other. Whoop. Faster and faster, crashing into each other so hard, the protons and the core, you can fuse together. So they slam into each other and join. When that forms, they form helium. When that happens, energy is given out and we end up with a ball of heat and gas. So we end up with a star. Smash them together, eventually join, turns into a star. Here we go. Here's something that I didn't realise. This does actually make sense. The sun's actually getting bigger and bigger and bigger all the time. The reason it's getting bigger and bigger is because the gases, hot gases, are pushing it out, are expanding it. It's like blowing up a balloon. But at the same time, thank you, Emily, at the same time, its gravity it's getting larger as well, and it's pulling it in. So if something's trying to expand, but gravity's trying to suck it in, what's going to happen?
It's not going to go anywhere.
It's not going to go anywhere.
So that way it doesn't get bigger.
So it doesn't get bigger, it stays the same size. Okay? Stays the same size. Until to glow and basically this new star is born. So when that happens, you've got the new star. When everything starts slamming together, we end up getting enough heat, boom, starts a star. Now, that there is the Eagle Nebulae. Now, when I say the Eagle Nebulae, what basically scientists are predicting, that those three things there will end up doing this. What's going to happen? Yeah. Each one of them will produce its own star. So you'll have 3 stars sitting in a row. If it all goes to plan. And secondly, what might then happen? Prediction, what could happen? If you get 3 stars close to each other, what could happen? They could join. Yeah, they could get sucked into each other. Or these things here could start to suck into each other.
So what happens if it's sucked into the stars?
Okay.
One big star.
Well, not originally.
No, if the 3 stars are sucked in, then it'd be one big star.
It could do. But I don't know why it didn't start with. But more importantly, guys, have a look at these tips. What do you notice about these tips?
They're all different.
They're all different. Are they different colour than down the bottom down here?
They're different color at the bottom, but then they go to the same color at the top.
So what? Yeah, but what do you think's happening at the top though?
More light
Why? What's happening?
because stars.
The star is starting to be born up the top here. Because the heat, they're slamming them together, releasing some energy. If it gets to enough stage, it'll instantaneously start to take off. It's a bit like when you guys get a match, you flick the match, you get some sparks. If it doesn't, if you keep doing enough, what should happen?
Go on fire.
Boom, it'll instantaneously light fire. That's the beginning of a star being born.
You know how you said they go online?
Yes?
Like that. Do you know the Orion's belt? Is that what
Same type of deal, but they're so far apart. But see, Orion's belt, we see them line up one beside each other. But in fact, one could be you, one could be Eli, and one could actually be over near the coffee shop.
Yeah.
But when you look at them in a straight line, what do they appear? Right beside each other. Okay, which is a problem with constellations, because if I shifted my position, it's no longer Orion's belt. All right. Here's a star bursting into life in the Carina Nebula. That's just about happening. You can actually see, for example, you can tell in there, you can see the energy basically, a bit like a fire with the smoke around it, isn't it? When it finally ignites, a lot of that dust and stuff really gets sucked in really quickly because the reaction is so powerful. Okay. There's another one. A firestorm of stars. When I talk about a firestorm, what am I talking about? How many stars? A lot. Not just one, maybe hundreds, maybe thousands of stars all at the same time being created. The distance, guys, the distance across here is huge. Beyond our comprehension, because you've got to remember each star is a sun, which could have its own planets going around it. All right, nearly finished. Now, they're actually talking about that section there. If you have a look at that section to the right there, it looks like fireworks. Okay, a whole bunch. This means at that stage there, that they call it the Hodge cluster, huge amount of stars have been formed in the last, oh, look at that, a few 10 millions of years. Now, can I say a word of warning here? You've got to be careful when scientists start using numbers like this. When they say a few tens of millions of years, it's guesswork. Because they can't give you an exact figure. They know it takes an extraordinarily long time, but a scientist has never seen the creation to the birth of a star, from the beginning to the end. It's not like, we have here, we can see a 9-month pregnancy in a person, we can see the beginning to the end. Scientists have never seen a star start and finish. They can see lots of stars along different stages along the way. There's lots of different stars, you've got the idea, but they've never, so they are estimating times. There's never been one record saying, oh look, on June 1901, we saw the cloud. Oh, 1950, we saw the that cloud turn into a sun. In 2013, that sun went out. In 100 years, never going to happen. In fact, in 100 years, you would not notice actually anything much occurring. Very slow process, which is why they say millions of years. Okay, what happens? Here's the important part I want to get for the rest of today. Nuclear fusion. What's nuclear fusion again, please, Maddie? What is nuclear fusion? where two or more atoms physically, not joined, physically combined to create what? A new atom. It could be two hydrogens make a helium, but it's not just like salt and it's not like sodium and chlorine come together to make sodium chloride. That's not fusion. That's just an ionic bond. Fusion is where you get the sodium and the chlorine, they smash together and there's only one atom left. But they've actually joined it together. Okay? To put it somewhere like this, it's a bit like putting flour and egg together and baking it. Can you pick the egg out after it's been baked? No, it's been joined together. Now, down the bottom here, the last dot point. The stars stay almost exact the same for a long time. Hydrogen changing to helium, about 10 billion years for a star like the Sun. So scientists estimate that 10 billion years is the life of our Sun, going from hydrogen to helium. Okay, hydrogen to helium. Now, you can get different colours. Blue stars are hot. Oop, go back in. Blue stars are hot. Smaller stars are less bright, cooler, and red. What's ours?
Yellow.
Ours is the yellow star, and we actually call it a red star
Why is red and yellow?
because it's the colour. It's like a Bunsen burner flame. What colour's the most intense? What's the hottest colour? Blue.
Why is red
Yeah, why is
actually
red
red and
yellow?
yellow?
Oh, I don't know. Okay. The hotter they are, the bigger they are, the quicker they're going to collapse, burn up. How's a star die? Okay. Have a read of that, guys.
What's that movie about a star? Maybe Star? Star something.
Star something.
And she's a star, and she comes down to
It's not real.
Sure. I think it could be.
Okay.
But it's really
Okay.
good.
Okay.
She's a
What's
star.
not real?
She's a star and she comes down.
Okay. What happens here, guys? At some stage, a star has to run out of helium. Has to run out of hydrogen. Hydrogen has to run out.
Lights and things.
You've run out of hydrogen, you converted it all to helium. Now, without the heat from the nuclear reaction, the stars, the gases stop expanding. Think about it. We had this thing here before where all the gases were expanding because you had this big nuclear reaction causing lots of heat, pushing the gases out. If the reaction stops, what's going to happen? It's going to start to fall back in on itself. Now that's okay. That's okay. Now, think about that. Come on, someone give me a possible thing. It starts collapsing on itself. You've got all this helium, big ball of helium there, and it starts to collapse. What's going to start happening then? Pressure again. Friction again. The atoms are going to lose their electrons again because they're going to be stripped because of all this heat. What's going to happen? Okay, so therefore a medium-sized star like our Sun swells and becomes a red giant, which means it's now combining helium and helium. What's number 4 on the periodic table?
Lithium.
Is it lithium?
I would assume so.
Lithium or beryllium? Someone have a check on their periodic table.
I reckon it's lithium.
Which one's it going to be? So if we have, sorry, I'll go back again, I'm too quick. So if we have helium plus helium,
It's beryllium.
and it's beryllium.
Oh, I was close.
Okay, so you end up with a star producing beryllium. Now, beryllium is 4. What's 4 plus 4?
8.
8. What's 8? 8's oxygen, so it ends up making, so basically what happens is, now, it doesn't exactly work like that. Now, here's a good picture. Here's a good picture. Have a look at that. See that little dot in the centre there?
Expanded a bit.
That's the Sun in its current size. It's a current size. As it shrinks, now because helium is twice the size of hydrogen because there's 2 protons, the sun starts to get bigger. And when it starts burning hydrogen, helium into beryllium, everything starts to get bigger. So you end up with this gigantic red giant, which means what's going to happen to us as Earth? We're dead. We've been burnt up and crispy fried.
Like in knowing how to say it.
Yeah.
Yeah. Okay. Now, Alan said to me, what is this AU unit? AU stands for astronomical unit. Can anybody remember what the size of the astronomical unit is?
Oh, is that the
The
little...
distance from? Yeah. So one
How does AU stand for that?
One astronomical unit equals the distance from Earth to the Sun. So the Sun is only 0.01 of the distance between us and now. When it gets to a red giant, it's 2 astronomical units. So in other words, if the Sun was there, now, that's where Earth would be. If that's currently the Sun there, double the distance from the Sun now, and that's the outer edge of the Sun. Who's lost what I'm talking about? Who's not too sure what I'm talking about? Currently this bit here I'm showing you now is the current distance that we are away from the Sun. That's 1 astronomical unit. The whole way across the Sun is 2 astronomical units, which means we're now going to double that size. So this over here may be Jupiter or something. So that's how big the Sun would be. Massive. Massive. Okay. Now.
Well, what happens to like Mercury and everything?
Oh, they're gone. Sizzled up, burn up. Gone. Okay. Rightio, have a watch. Alan said, what happens then? Well, as the centre collapses, the star becomes hot again, eventually getting hot and hot enough. Nuclear fusion with helium as the fuel, we just talked about. The helium now fuses to form a carbon nuclei. The red giant shrinks and the star looks normal again. So we're using fuel again, different type of fuel. Doesn't last as long because we've only got half the number of atoms. Because we've gone from this many to halve them. Every time you make new ones, it halves them out because it keeps joining them together. Runs out quickly, forms a red giant again, basically becomes a planetary nebula, and it's only about 20% of the original star. And then the star ends up doing that, but
Can you put that back?
that is pretty, isn't it?
I don't
Okay.
The one on the right.
At the very end of this entire sequence of stuff, it can become a white dwarf.
Darn.
What if it's one?
Okay, which means, sorry?
How long would it take us?
Billions of years. Billions of years. Billions. Now,
Wait, what happened to Lois alive?
Isn't it when the white dwarf like dies, it becomes pure carbon?
can do a couple of things. There's a couple of things, depending on size. Okay, now a white dwarf, guys. A white dwarf is a star that's basically running out of fuel. So it's a bit like you having a raging campfire and not putting any more fuel on it. It eventually dies down, still produces light, but not much heat. Does that make sense? So it's just running on empty. Now a couple of things can happen. It can either become a black dwarf, which means it just goes out, and then you can't see it any longer. Or it can become there's a white dwarf in the centre of that one. Or it can go to what we call a supernova. And a supernova is where there are really big ones and they basically explode themselves. They just blow apart. And there was a supernova about 10 years ago that was seen in the sky. They were watching it one day, and the next day it came back and there's a supernova. And a supernova is basically, let's see if I can find one here in the slide here.
Can you like go on YouTube and type up supernova, see what comes up?
Nearing its end. There's a whole bunch of stuff here.
There was one.
Yeah, that's a supernova. the Crab Nebula, blown itself apart. And then he gets to there because they're super big. They are supernovas. You can see in the centre here, what would you describe happening to that one there?
It's exploding.
It's exploding. It's going. Who'd agree it looks like it's going in all directions?
Yeah, it's exploding.
So basically what they do is they run out of fuel and they collapse on themselves. It's a bit like a building. When you've got these high-rise buildings, they blow up. They all collapse, and what happens at the very base? It all shoots out to the side. So it collapses on itself, gets in the centre, and just goes bam, boom, and just reacts and blows apart. And that's it. And once it gets there, guess what happens again? It all starts to do the whole process of gas clouds, and nebulas are gas clouds, which means the gases start to come together again.
Oh, is that, and it doesn't turn into a dwarf after supernova?
It depends how big it is.
So if it's really, really big, will it? That one
You know, if it's small, big ones will make supernovas.
No, that's my question.
They might turn back into another star and turn into a
Now,
So are there videos we can watch of it?
yeah, we can do. We'll do that.
I
Okay.
picked that one.
I'll stop after this one. If a star collapses and forms a supernova, it explodes. Huge stars, 1.5 to 3 times the size of our sun, shrink and form a neutron star. Neutron stars are basically dead stars shooting out neutrons. Or, if you get a star 3 times the size of ours, it can form a black hole. Now, a black hole is not a hole. A black hole is just a star that's collapsed on itself and shrunk down, like it's running the fuel. So it's no longer trying to expand. The gravity is pulling it all back. It collapsed on itself and it's so packed together, it didn't explode, didn't blow itself apart. It stayed there. But unfortunately, what it's doing now is it's such an intense mass, it starts to suck everything in towards it. Which means they call it black because even light gets caught in its gravitational field. So in other words, if you had a torch beam, if my iPad here was a black hole, and you could see a light beam, instead of the light beam going straight like that, the light beam would actually curve and go straight into there. The gravity, because light is particles, and it actually gets sucked into it. You cannot, it's been estimated, now, as I said, the word estimated, that if the Earth was caught into a black hole, every gap in the atoms, because you know atoms have gaps in them, if they all collapsed, the Earth would shrink to the size of a pea. So we're not losing anything, we're just crushing it to the size of a pea. And that's how much space is left, that's how much space the Earth would take up. So,
Oh, I see what you mean by the hourglass.
so the birth and death of a star takes millions of years. Basically, when it gets to the death of a star, it rebirths itself again. Black holes just keep circling around the universe. Alright, so birth of a star and death of a star are complete reverse, but they actually end up recirculating around. Alright, now,